Greetings and welcome. My name is Abdul Hakim Al Gamouni, and this video to present journal paper presentation for Sensor Awards 2023 International Research Awards on the Sensing Technology. The paper with title Flexible Joints for a Grid-Based Multi-Stable Composite Morphing Skin by Abdul Hakim Al Gamouni, XZ, and Hikmat Al Gambari, Department of Aerospace Engineering at Ryerson University, Toronto, Ontario, Canada. This presentation consisting of three parts. I'm going to start with collection covering problem statement and contribution. Then the second part has three subsections, each one corresponding title in this paper as shown in the right side of the slide. The first one about design and analysis grid multi-stable composite surface for a morphing skin. Second one about experiment verifications. And last one about design different layouts for real applications. I want to finish this presentation with some concluding remarks and future works. As we know, the morphing structure are significant research area in engineering industry, especially in aerospace and aircraft design. The most challenging design requirement for morphing structure is a skin which presented in plan complaints and out of plan stiffness. The bistable composite laminate are considered as a good candidate for achieving a morphing skin due to their ability to maintain the second chip without any external energy. For a high degree of multi-stability, a high number of bistable batches is needed to connect it as continuing surface as shown in the right side of the slide. Small number of studies have been presented regarding a multi-stable morphing skin. Until 2019, only a high degree of multi-stable composite surface in series were presented. After 1 year, the new idea for designing a high degree of multi-stable grid surface were reported. The first experiment investigation was by Wong and others. Then me and co-worker presented a new method to design a grid multi-stable composite surface. Our idea to design a grid multi-stable surface show limitation of stable states for moving surface. That means that a maximum number of stable configuration for multi-stable surface cannot be achieved due to a high interactions between bistable batches at linking edge on the surface. For this reason, a new idea for connection bistable batches is presented in this thesis, this study. We presented a surface consisting of cross-ply bistable laminate with the flexible strip in between as a continuing surface to reduce the interactions between bistable batches. The objective of this study is divided in two steps. We start by design 2x2 grid composite cross-ply batches with the flexible strip in between, as shown in the figure. Then we fabricated the case study of 2x2 grid composite cross-ply batches. The contribution of this paper is are summarized as listed. One comprehended the multi-stable behavior of multi-batch surface, understood the influence of symmetric and asymmetric bistable of batches on the number of states for the surface, achieved the multi-stable surface by reducing the interactions between bistable composite batches, developing the connection zone between bistable batches by introducing flexible joints in between. And last one is design a grid multi-stable surface consisting of n bistable batches possessing to power n stable configuration. To design multi-stable hybrid skin, we started by model the 2 by 2 bistable composite patches connected in grid with the flexible strip in between as continuing surface. As shown in the right side of the slide, each batch is designed to have two square layers. Each batch has stocking sequence is 0, 90, or 90. The carbon fiber pre-brick is used as a material for composite batch. And aluminum alloy is used as a material for flexible strip in between these batches. The flexible gap between batches is designed to be variable by increment 10 millimeter in order to reach a maximum number of states for the panel. As shown in the right side of the slide, the length and width of composite batches is defined by the length of panel minus the width of flexible strip in between along X and Y direction respectively. To model the multi-stable composite batches, we employed the finite element using abacus. 5 main steps to analysis panel structure are presented. We start by geometric clean up and simplification, material definition, meshing using the type of element and nodes, loading and boundary condition. Then we used the static analysis for nonlinear geometry model to get the first stable configuration for the panel. After that, we applied additional boundary condition and loading to reach another stable states. In this study, we used three different cases, three different stocking sequence cases, as shown in the right side of the slide. The first one is polar symmetric surface with opposite cross-ply laminate. The second one, polar symmetric surface with same bistable batches. And last one, axis symmetric surface with opposite bistable batches. For result, we started by consider the panel 1 model. Polar symmetric bistable surface in order to study the effect of flexible strip on number of stable configuration. We use, as we said before, we use the step increment 10 millimeter in order to select reasonable flexible width between bistable batches for achieving a maximum number of stable configuration over the surface. As shown in the right side of the slide, figure in the right side of the slide, theoretically the panel has 4 bistable batches, should show a maximum of 16 stable configuration. As a result, at the width of flexible strip is 0 millimeter, no flexible strip means no flexible strip between bistable batches, we get only 2 stable configuration. Then after increase the width of flexible strip between bistable batches to 10 millimeter, we get 6 stable configuration. Finally, we get the maximum stable configuration for bistable batches, which are 16 stable configuration at 20 millimeter width of flexible strip. That means that the flexible gap width between batches must be 24% of batch length for achieving a maximum of stable configuration for the panel. For experiment verification, we start by fabricated 2x2 multi-stable composite panel. We start by lay up batches layers and strip layers. Then we apply the vacuum pump system to release the bulk between layers. After curing the multi-stable surface with different bistable batches at 135 centigrade for 90 minutes, we get the preferred states for the panel for the protection of panel. As a result, for the panel 1, we get the 16 stable configuration that has a good agreement with finite element result. And also we get the 16 stable configuration that has good agreement with a finite element analysis. For the panel 3, we get only the 7 stable configuration has a good agreement with finite element analysis. Other 9 states are merging states similar to one of these 7 states. That means that after removing the constrained load on the driving patch on the surface, the system will jump back to one of 7 intermediate states as shown in the figure on the right side of the slide. This figure shows how energy is moved for all the states after removing the load on the driving patch. For application, we model 2x2 grid multi-stable hybrid surface between wing and winglet surface. We use it to different stocking sequence on the panel to find the cant angle for the wing. We start by polar symmetric batches with same bistable batches on the surface. We get the 3 different positions for winglet. Also, we use the axial symmetric panel, and we get the 3 different positions for winglet. The other application for grid multi-stable hybrid surface is used as a circular flat part to find the potential multi-stable configuration for antenna reflector, as shown in the figure. We use the third different stocking sequence, which are polar symmetric batches. And we get the 16 stable configuration for this novel reflector surface. Concluding remarks and future work, we start by conclusion. A new method to design multi-stable composite surface has been presented. Finite element model was used to predict the stable configuration of Morphing surface, and experiment verification was provided for validation the stable configuration. The result proved that it's possible to design a highly multi-stable surface using strip in between bistable batches. The achievement of maximum number of stable states depends on the width of flexible strip between bistable batches. A maximum number of 16 stable states was achieved in this study using the structure case of a grid multi-stable hybrid surface. A more adaptive multi-stable panel can be designed through laminate tailoring to suit realistic surface moving application. For future work, the effect of aerodynamic force on multi-stable surface will be investigated as a part of loading analysis. Thank you for listening. For more information, please connect me at this email.